Have you ever wondered how bottle caps are made? Have you ever noticed that the inside of most bottle caps are not direct spirals, but rather have broken up, non-continuous threads? For bottle caps to get their shape, plastic must be melted and formed by a mold. It is no surprise that the mold itself has a complex design process. Our presentation today encompasses a detailed overview of injection mold manufacturing, which is the process of designing and fabricating the reusable tool that shapes and cools molten plastic into a finished part, focusing specifically on manufacturing a mold intended to produce these plastic bottle caps. To understand injection mold manufacturing, we must first understand the process of injection manufacturing. First, plastic pellets are fed into a hopper where they enter an Archimedes screw or plunger system that heats and melts the material through shear and heating bands. The molten plastic is then injected into the mold's internal cavity, which replicates an exact negative of the part to be designed. The plastic cools and solidifies, retaining its shape. It is then ejected and the cycle repeats. This process is particularly useful in mass production due to its durability, precision, and ability to quickly produce identical parts, even multiple at once, with consistency and accuracy. This is essential for high-volume items such as bottle caps. The mold is the heart of the process. Everything from the injection of molten plastic to ejection of the final part relies upon the design of the mold. The mold determines the geometry and dimensional accuracy, quality, cycle time, efficiency, durability, and performance of the part. Understanding the mold design is crucial for optimizing production to keep manufacturing costs at a minimum while maintaining the high-volume demand. Injection mold manufacturing began in the 1870s when John Wesley Hyatt created the first molding machine, which used early thermoplastics to produce billiard balls. Early mold designs were operated by hand and used two-plate designs. As technology advanced, three-plate molds and hot runners, which keep the molten hot to prevent premature cooling as it is injected, were introduced. In the early 1990s to 2000s, precision and accuracy of the mold design were drastically enhanced as CAD, CAM, electrical discharge machining, and CNC machining advanced. These molds are typically made of hardened steel or aluminum. However, with recent advancements in technology, there are new ways of making molds for testing purposes. Before designing the mold, we must understand the geometry, functionality, and requirements of the bottle cap. A standard plastic bottle cap includes a skirt, which is the ribbed cylindrical outer wall of the bottle cap, internal threads for screwing and unscrewing, smooth, flat-top sealing surface, tamper-evident bands near the bottom of the cap, and some caps have external ribs for gripping. These parameters are modeled in CAD and the mold is formed as the negative of the cap.
The core and the cavity are the two primary components that make up a mold's cap. The intricate internal geometry of the cap, such as the threads and sealing ring, is formed by the core side. The smooth exterior, knorrels, and logos are all shaped by the cavity side. A separating line or the division between the cavity and the core must also be selected. For a bottle cap, we want that line to be in a location that minimizes apparent marks, permits clean formation of the threads and sealing surfaces, and facilitates appropriate ejection without causing damage to the cap. Internal threads, draft angles that allow the cap to come off, and the shrinkage of materials like HDPE or PP as they cool must also be taken into consideration. In order for a tamper-evident band to be modeled and released without undercut issues, that geometry must also be designed. All of this is finally recorded in CAD, where the negative mold geometry surrounding the bottle cap is modeled. We cannot create a mold that is manufacturable, long-lasting, and consistently produces high-quality parts until we have a thorough understanding of the cap specifications and features. Now that we know what our cap will look like and have our basic mold shape in CAD, it is time to add key features to the mold. First, we must determine how many caps are to be produced per cycle. Then we must determine which metals we want to use for our mold. The mold material impacts how and where to incorporate our runners and gating systems, which are pathways that allow the injected material to enter the mold, as well as cooling channels, which are pathways where coolant fluid removes heat from the mold, allowing the part to cool both quickly and uniformly. The speed at which a cycle can occur depends greatly on this cooling process. Finally, we will look into methods used to eject the part from the mold, specifically how it's done for bottle caps. Within the mold, there are runners that guide the injected plastic to the cavity. In a multi-cavity mold, there is a network of runners that go to each part and connect to a main runner where the plastic is injected to. This is called the sprue. There are also two types of runners, cold and hot runners. For cold runners, the injected plastic will cool within the runner and then has to be removed from the part, which adds to the cycle time. Hot runners maintain the plastic melted between each injection cycle and leaves no excess that has to be removed from this part. This is highly beneficial for a high volume production such as caps that want to shorten the cycle time as much as possible. A runner won't directly run into a cavity, instead it will pass through a gate. A gate is an entrance to the cavity and is smaller than the runner. The plastic will enter through this gate and leave a less noticeable break-off point. For caps, the break-off point is found in the middle inside of the cap. Inside the mold, the plastic has difficulty cooling because of the heat trapped inside. In order to improve the cooling process, cooling channels are machined into the mold and follow the shape of the cavity. However, this is difficult to do, especially with complex geometries. In cases like this, the mold is sliced into sections and the cooling channels are machined section by section in order to better fit the geometry. Vents are also machined into the injector runner surface interface to allow air to escape the mold. These vents are usually microns thin and there is no worry of the molten plastic seeping through because it is too viscous. Once the mold has cooled and the core has retracted, it is time to eject the part. There are multiple methods in which this is done. Ejection pins are one of the most common, and as it sounds, they are pins that come from the core insert of the mold that push the part off of the core. Stripper plates are a separate plate that ride on rails between the core side and the cavity side of the mold. The stripper plate applies even force to the part being ejected in order to avoid deformation and damage. They are used when pins are inadequate or when the client doesn't want marks left on the part. Finally, we have rotating cores, which act as an insert that the plastic molds around. Instead of pins or a plate, this insert will unscrew from the molded part and release it, leaving a precise and accurate threaded geometry within the part. Caps are usually designed with non-continuous shallow threads, which allow for slight elastic deformation. This allows for the use of a stripper plate to remove multiple bottle caps without much worry of deformation. The high cavity number for bottle cap molds means ejector pins will be inefficient and difficult to implement. Thus, the use of a stripper plate is preferred.
We begin mold fabrication by selecting the right stills for each component. On the right side of the slide, you can see the two most commonly used materials, P20 and H13. P20 is a pre-hardened tool steel that machines easily and holds good dimensional stability. These qualities make it ideal for the mold base because the base plates are large structural components that do not experience extreme heat or wear during molding. H13, shown in the second column, has much higher hardness, strength, and thermal fatigue resistance. For that reason, H13 is used for the core and cavity inserts, which are the surfaces that form the plastic part and take the full injection pressure and heat. Once the materials are selected, the steel blocks are cut to rough size and trued so the CNC machines have accurate reference faces. Rough machining then removes most of the excess material and begins forming the early shape of the cavity and core. The process diagram at the bottom helps show the full sequence. It begins with drilling and grinding, moves to rough machining, and eventually transitions to the finishing stages, such as EDM, polishing, and laser engraving. This illustrates that rough machining is only the first step in a much longer, more detailed fabrication process. The layout on the right shows where each material is used in the mold. P20 is chosen for the mold base plates, while H13 is used for the high wear, high temperature inserts highlighted in red. After the roughing stage, the H13 inserts are sent to a controlled furnace for heat treatment. This increases hardness, wear resistance, and thermal stability, which are essential because melt temperatures can exceed 200 degrees Celsius and injection pressures are extremely high. Heat treatment causes slight distortion, so once the inserts come out of the furnace, they receive a light cleanup in a machining pass. This restores the critical dimensions and prepares the components for final precision machining and EDM. With heat treatment complete and the inserts restored to spec, we now move into the high accuracy stages of mold making, where CNC machining and EDM create the final geometry. Once heat treatment is complete, we move into the precision machining stage. This is where the inserts regain the accuracy that may have shifted during heating and cooling. The small finishing tools used in CNC milling. These tools remove only a thin layer of material, leaving the surface smooth, accurate, and ready for final detailing. Because the inserts distort slightly during the heat treatment, precision milling and surface grinding restore the geometry to tolerance. These steps restore flat surfaces, sharp edges, and proper alignment so the inserts fit correctly into the mold base. However, rotating tools have limitations. They cannot reach deep pockets, narrow corners, or extremely sharp features, which is why EDM becomes necessary. In the second image, you can see EDM in action. Instead of cutting metal with a rotating tool, EDM uses controlled electrical sparks to remove material. This allows the toolmaker to create sharp ribs, deep cavities, sealing threads, and other fine details that traditional CNC milling cannot reach. For molds such as bottle cap tools, where every cavity needs identical threads and sealing surfaces, EDM ensures consistency across all inserts. Once the geometry is complete, the inserts move into the surface finishing stage. Polishing removes tool marks and smooths the surface so the parting line seals properly. Even small imperfections here can lead to flash on every molded part, so polishing is an essential step. Laser engraving adds textures, logos, part numbers, or grip patterns without disturbing critical dimensions. The surface finish created at this stage transfers directly to every molded part, so accuracy is extremely important. Together, precision machining, EDM, and surface finishing transform the heat-treated steel into a fully defined mold insert. These stages ensure the mold meets its final dimensional requirements and can produce clean, consistent parts during high-volume production. With the inserts fully machined, polished, and engraved, they are ready to be installed into the mold base. This leads us into the assembly and fitting stage, where each component is positioned, aligned, and tested for proper operation. Now that the mold components have been machined, heat treated, and finished, the next phase is assembly and fitting. This is where the individual inserts, plates, and mechanisms come together to form a complete, functional mold. The first image on the right shows the basic setup of the core, cavity, and mold base, which is where assembly begins. The core and cavity inserts are placed into the mold base using guide pins, bushings, backing plates, and mounting screws. These features ensure that each insert seats squarely and closes cleanly against its matching surface. If the mold uses a hot runner system, the heated manifold and nozzles are installed at this point. These components must follow a specific torque sequence so they expand evenly once the mold reaches operating temperature. Next, the ejection system is assembled. This includes ejector pins, sleeves, lifters, return springs, and the ejector plate assembly. The ejector plate is cycled by hand to make sure it moves smoothly without sticking. Once the inserts and ejection system are installed, the mold halves are brought together for alignment. Alignment is one of the most critical steps. The mold must close with zero gaps because even a few microns of mismatch can cause flash, short shots, or sealing issues. Toolmakers use spotting compound or blue ink to check shutoff surfaces, and they confirm parting line flatness with feeler gauges or CMM measurements. The middle diagram on the right highlights the runner system, which depends on this precise alignment so the molten plastic flows evenly into every cavity. The vents are also inspected here. These vents are extremely shallow, so they must allow air to escape without letting plastic leak. Once alignment is confirmed, the mold moves into fine tuning. The injection system is adjusted so parts release cleanly without drag marks or pin flash. Vents may be polished or slightly open to improve venting. Cooling lines are tested for uniform flow and leaks, since uneven cooling can lead to warpage or inconsistent cycle times. Any issues in venting, ejection, or cooling are corrected through small spotting marks, polishing passes, or minor insert adjustments. The final stage is verification. The mold is dry cycled to confirm smooth opening, closing, and ejector motion. It is then placed in the ejection molding machine for its first trial shots. These early parts are inspected for surface quality, filling, sealing, and dimensional accuracy. If anything is off, adjustments are made until the mold produces consistent, defect-free parts. Once the mold reliably produces good parts, it is ready for full production. Assembly and fitting are essential because they determine how smoothly the mold will run and how consistent the parts will be in high-volume manufacturing. With the mold fully assembled, aligned, and producing consistent parts, the final consideration becomes how to protect that performance over time. This leads us into our next topic, where we look at maintenance and the steps needed to extend mold life.
Today I'm going to talk about why mold longevity and maintenance really matter in injection molding. First, it helps remember that the injection mold is not just a block of steel, it's a highly engineered, expensive tool that is expected to run thousands or millions of cycles while staying accurate. How long it actually lasts depends on several things. The steel grade, how much heat it sees near the cavity surface, the polymer being molded, and how well the cooling system is designed, and how consistently the mold is maintained. Research on plastic mold steels have been shown that the temperature right near the cavity surface can spike much higher than you might expect from the polymer's melt temperature. In some tests, the surface layer of the steel reached over 500 degrees Celsius during the simulated molding conditions. At those temperatures, the steel at the surface starts to lose hardness over repeated cycles. Once that thin layer softens, wear speeds up. Edges round off faster, dimensions drift, and you can see more problems like flash, mismatched parting lines, and eventually part defects. This is one reason why surface protection is such a big deal. The thin PVD coatings, things like titanium nitride or chromium nitride, can act like armor to the surface of the mold. Studies show that these coatings reduce abrasive wear, adhesion of the melt to the steel, and corrosion from the aggressive polymers in processing conditions. In simple terms, they make it harder for the plastic to stick, harder for the steel to scratch, and harder for the surface to rust. This combination helps the mold keep its hardness and shape for more cycles, which directly extends mold life. But coatings and steel choices are half the story. The other half is mold maintenance. Good maintenance is more than just wiping off mold off between jobs. It includes regular visual inspections of high-stress areas like parting lines, gates, and thin features, checking hardness or monitoring critical regions over time when the mold runs hot, processes abrasive glass-filled materials, polishing worn surfaces to restore smoothness and keep friction low, replacing worn components such as ejector pins, guide pins, bushings, springs, and seals before they fail in production. Restoring vent depths if the vents get clogged or peened over so trapped air can escape and doesn't cause burns or short shots. Steps are ignored. The effects show up quickly. More part failures, more sticking, safety risks from damaged mechanisms, and a lot more scrap and downtime. In the worst cases, a mold was designed to run for hundreds of thousands of shots, might have to be rebuilt or retired much earlier simply for it wasn't cared for. The research on hardness loss makes it clear that once the surface layer of the steel starts to soften and wear away, the problems accelerate. Work on PVD coatings show that if you protect the surface and keep it clean and maintained, you can dramatically slow that damage down. So the big takeaway is this. Mold longevity is controlled by both the environment and the mold it runs in, heat, pressure, polymer type, and the protection we give it through the material and coating choices. The mold maintenance inspections, polishing, replacing worn components, and keeping vents and surfaces in good condition is what keeps the expensive tool working the way it was designed. When we combine the smart choices in materials and coating with the consistent preventive maintenance, we're not just being nice to the mold, we're protecting a major investment and keeping a part quality high over the entire life of the tool.
To recap, the mold is the heart of injection manufacturing. The mold itself requires its own manufacturing process, which is very extensive and intricate. The mold is designed in CAD as the exact negative of the cap, and this forms the internal core and external cavity. Conformal cooling systems, hot or cold runners, gates, sprues, and vents are implemented into the CAD design. The mold is then fabricated using a series of large and micro-scale techniques to achieve a design that produces a perfect bottle cap every time.